All right. Well, welcome. Thank you for joining again. We have, that's the wrong thing. We have an exam coming up on Wednesday. And, I've been a little bit apprehensive about how these exams were going to go, except for that I gave an exam on Friday to my engineering economy class, and it went totally smooth. There wasn't a single issue. Nobody had problems. Everybody uploaded their exam on time. I thought there was going to be at least one screw up, but no, it was smooth, and so I think our exam is going to be smooth as well. Now I'm aware of the fact that some of you who are in the hydrology class have an exam Wednesday morning. So, I mean, when it rains, it pours, right? Everything kind of happens at once sometimes, and this coming Wednesday is going to be one of those times where you'll have the hydrology exam in the morning and you'll have the hydraulic exam in the afternoon. For this hydraulic exam, I'm going to give you from 1 p.m. until 4 p.m. And so the exam will be posted on Blackboard and will be emailed to you at 1 o'clock. And then you'll have 3 hours to work on it. So you'll need to submit it by 4 o'clock and you'll upload your files to Blackboard, meaning anything that's a hand calculation, you'll make a nice, clear, sharp, black and white PDF file of that, probably using Cam Scanner. And then if it is an Excel file, you'll upload that Excel file. If it is a problem having to do with water gems, then you would create the archive. If you're sharing any of your files, you need to create like a package that includes the database file and the water gems file. So there may be a question where I ask you to use your newfound skills and strengths in water gems. So be prepared for that. The exam is going to be from 1 to 4 on Wednesday. It's open book, open note. You can use your previous homework assignments. You can use the project files that you've been working on. So any resource that you've got there in your binder or there, in front of you, except for that you have to work individually. And I'll ask you to sign a statement on the exam cover sheet where you say that you worked on it alone without anybody else's input and assistance. So a week after that, homework 10 will be due, and homework 10 includes some questions having to do with spillways and weirs that we're going to be talking about today. And then the final project report is due on Monday the 20th. And so today you've turned in your reservoir sizing, and I'll look at your reservoir sizing, give you any feedback or notes that's needed for that. And then the final project report is where you fix your demand estimation. And if you didn't already in the draft submission for phase 1, if you didn't have a write-up, you'll need to include a write-up explaining your assumptions and the method that you use to come up with your demand estimation. And so you fix up part 1, you make any adjustments to part 2. Basically, you're updating the drafts for the first 3 phases, and then you're also adding in the cost analysis that's described in the handout. And so then the final project report will be due on Monday the 20th. All right, so are there any questions on the announcements? Okay. Feel free to interject with questions, and if I don't happen to notice a comment or a question that you've typed into the chat box, you can send me an email after class, and I'll encourage you to not be shy and turn on the microphone if you have a question about something or if I need to explain something another time. All right, we're talking about spillways and weirs today, and this is an extension of some of what we can do with specific energy. So far, we've been using specific energy analysis to answer the question, what will be the new depth downstream in response to some sort of a change? Like if the channel is getting wider, or if the channel is getting narrower, or if water is having to flow up over an obstacle or flow down off of a step. We've looked at a whole lot of problems asking the question, what's the new depth downstream when there is a specific energy analysis. Now, spillways and weirs are a way to use specific energy analysis to analyze flow conditions. And just as an illustration of that, here is a a watershed map for the Columbia River. And so the Columbia River is an extremely long and complex river system that extends through Canada and several U.S. states. And you can see the contributing area is highlighted in yellow there. And the Columbia River passes through Portland, Oregon, Vancouver, Washington, not to be confused with Vancouver, Canada. But this river network, which is really long and important both for navigation, barges go up and down the river to take agricultural products to market, but it's also really important for irrigation. That network is controlled in large part by the Grand Coulee Dam on the Columbia River. And so it's a really long dam system, and what we're going to be looking at today is equations that answer the question, what's the flow rate over the top of a dam spillway? And so the spillway is just one of the several different ways that water can come out of a reservoir on the upstream end of a dam like this. And so most of the water is going through a power plant. A big part of the benefit of the Grand Coulee Dam is that it's generating a significant amount of electricity. Most of the electricity that's needed in the northwest part of the United States is generated by the Grand Coulee Dam. So it powers Seattle almost entirely, for example. So they don't need coal-powered plants, they don't need nuclear in Seattle, they're using hydropower. And so most of the water is going to flow through the turbines that are generating electricity, and it's only during rare occasions that water would go over the top of the dam and flow down this front spillway, because when water is flowing down the spillway, you're not able to capture the energy. It's just energy is being lost. And so it's only in an emergency situation, when it's been extremely wet in the upstream area, when there's just been lots and lots of rainstorms in the upstream area and there's more flow that has to be discharged than can go through the electrical turbines, then they would send water through the spillway. And so here's a periodic release of the spillway just to to test it out. They'll occasionally send water through the spillway and down the front face of the dam there, and water's moving very fast. It's a long, steep, very tall structure, and so flow conditions are super critical when the water is going down the front face of that spillway. Later on, after the exam, we're going to start talking about hydraulic jumps, which is the transition between supercritical flow and subcritical flow. So we're not quite there yet, but just to give you an idea, it's flow down the front face of a spillway that often causes the hydraulic jumps that we're going to be studying in a little bit. But for today, what we're focusing on is, for a watershed area like this and for those spillways, how would we know what flow rate is coming down the spillway? Like, what are the governing equations that relate the height of the water above the spillway, the length of the spillway, and the flow rate that we see? And so just to give you an idea, the length of the spillway, that in the equation that we're going to look at today, L, is the distance along this top distance across the top. And so L is kind of a perimeter distance that the water is flowing down the face of. And from the side view here, you can see that H is the height of the water above an imaginary sharp crest. Now they have a pretty specific shape. It's called an OG spillway, where they have a curvature that transitions the water so that you're losing as much energy as possible in the hydraulic jump, but so that there isn't a rapid transition in the velocity prior to that, because it would cause scouring potentially of the spillway. So you'll notice that there's a shaded in segment here that looks like kind of a sharp crest, and that's just an imaginary sharp crest. That's not an actual physical difference. You could think of it all as just a single continuous slab of concrete, although in the center there they may have buildings having to do with like the pump plants or the turbine building and so on. But from a hydraulic standpoint, the height of the water above this imaginary crest can be broken up into the height that's actually the height above the physical spillway crest, and so that's h sub d, and then normally below that physical height of the spillway. So the gap distance between the two is the distance between the imaginary sharp crest and the physical elevation of the spillway crest. The gap between the two is approximated as 11% of the overall height above the imaginary sharp crest. So, excuse me, in the traditional units, then the flow rate would be 3.32 times L, where L is length in feet, H is the height in feet, and then the flow rate that we get out of this is cubic feet per second. So this is not a dimensionally homogeneous equation. This is non-homogeneous. This is an empirical equation that includes a loss coefficient, but it allows us to predict how high the water level would be for a certain flow rate. And we'll look at other types of flow measuring devices today, but remember that this all ties into specific energy. So we're looking at a location upstream and a location downstream. And so the upstream location would be before there's drawdown in the vicinity of the spillway crest. So upstream, there's a certain water elevation, h, above this crest. And then downstream, what you've done is you've exchanged some of the velocity, you've exchanged some of the water depth for additional velocity. So you'll notice that the shape of the water curvature is it's going lower and lower along that spillway crest. So just to show you how some of these calculations work together, let's do an example where if we know the physical length of the spillway is 300 feet, and so then that would be L, and it's used to control the depth of the water in a reservoir. And we would expect that in a 100-year storm, the spillway has to flow 38,000 cubic feet per second. And in the vicinity of the upstream water surface, there may be buildings or other structures upstream that mean we don't want the water elevation to get above 4,350 feet. And so we're trying to figure out what elevation of the spillway crest should be selected to keep the water elevation no higher than 4,350 feet. And so in other words, we want to find out if the water level is at 4,350 and you know L and you know Q, then what would be the corresponding H sub D that we will subtract out to find the elevation of the spillway crest. Okay, so I'm going to pause for a moment and give you a chance to substitute in the length and the flow rate and solve for H sub D so that then we could calculate what's the water elevation that should be used for the spillway crest. Alright, Farrah's got it, but I'm not sure. I bet it's right. Let's take a look. Okay, so we know the flow rate going over the top of the spillway is 38,000, the length is 300, so we rearrange the equation to solve for H sub D. So remember, the H sub D is talking about the distance from the top of the spillway crest up to the water level upstream. So that's not going to be the elevation of the water directly above the spillway crest because it draws down in the vicinity of the spillway, but it's the water elevation upstream before that drawdown occurs. So solving for H sub D, it's 10.06 feet, which means if we subtract 10.06 from the given water surface elevation of 4,350, then that means that we should build the crest at 4,339.94, and then that'll ensure that the water upstream, even when we have 38,000 CFS going over the spillway, that the water level doesn't get higher than the maximum allowed 4350. So then to make that happen, at what elevation should the spillway crest be built? That's 4339.94, but we can also ask the question, where is the theoretical Weir crest? And so, you know, like, what is the elevation of that theoretical sharp crested Weir? So we could look at it the other way, and instead of solving for h sub d, we just solve for h. So that's 11.33, which means that the theoretical theoretical Weir crest is at 4338.67. All right, so I only really asked you to calculate this first one in the example. Are there any questions about what a spillway does or what this equation does? A spillway is kind of just the emergency way to get water out of a dam. Even a very small dam, like the kind that someone would have like a pond at their house. My parents have a lake at their house, and they have a spillway, but I've never seen water going over the top of it because it can cause quite a lot of scour and erosion, and it over the long term can threaten the dam. And so normally you'd want the water going some other place, but the spillway is kind of an engineered structure that the excess flow can go on a temporary basis. All right, so that was one.
Oh,
go ahead. Is there a question?
oh, yeah, I'm sorry. And you may have covered this earlier, but I'm not sure why you used H sub D instead of H. I think I may have missed what H sub D is.
All right. I'm glad you asked. That's an important distinction to make. So H is the distance. Oh, L. Okay. Now I have a laser pointer. H is from the theoretical sharp crest up to the water surface, whereas H sub D is from the actual physical height of the spillway. So the spillway is the actual real thing, whereas the sharp-crested weir, a sharp-crested weir is a structure that's often used to manage and quantify flow, and so the fact that this spillway behaves a little bit like a sharp-crested weir is of significance if we wanted to understand how the spillway is behaving. But like if you're actually telling a contractor what elevation that crest should be at, then you need to use H sub D, because H sub D is from the water level down to the physical elevation of the spillway. Does that answer your question?
So it's the number that just accounts for that sharp component?
The H does.
Weir?
Yes. The H is to the sharp crested. H sub D is to the actual spillway crest.
Okay. Thank you. I get it now.
Yep.
Or I think I do.
And congratulations for using the microphone, brave soul. I wish everybody would do that. It's quicker than typing your questions. All right. Are there other questions before we move on? Okay. This is a broad-crested weir. And if we were meeting in person, we would walk down into the hydraulics lab today and we would look at the broad-crested weir in our flume. Unfortunately, we're not going to do that. And worse yet, we don't get to have hydraulic jump day this year. And that is a real problem, because hydraulic jump day is kind of like the highest holiday in the hydraulic engineering calendar, where you observe the hydraulic jump and write poems in honor of the hydraulic jump and enjoy hydraulic jump cake, but we don't get to do that this year because of COVID-19. So we'll just look at pictures and videos and stuff. So a broad-crested weir acts by inducing critical flow. And so think of, if this block wasn't in the channel, the water would just be flowing along freely. But what this block did is it forced the water upstream to pool. And so the water got up to this level. It got deeper because there was an obstruction in the way. And so the water is getting deeper and deeper and deeper until it doesn't need to get deeper anymore, and it reaches a new equilibrium where the flow over the obstruction is equal to the flow that water is being pumped into this channel. And so it's in equilibrium right now. And does anybody know? Now, obviously, we have a couple of different depths here. You notice that there's a curve. And so part of it is drawdown as the water goes over the edge. But what I've learned over time is that if you have the depth about in the middle to 2/3 of the way along the distance, then what you will find is the critical depth. So the pooling upstream, it keeps getting deeper and deeper until there's just enough energy upstream to force the most efficient flow condition over the obstruction, and that is the critical depth. So what we're looking at right here is critical flow over the obstruction, over the Broad-Crested Weir. And so here's a Broad-Crested Weir illustrated with specific energy. So what this is showing is that over the obstruction, critical flow is induced. And remember that when we have critical flow, the depth is 2/3 of the specific energy, and then 1/3 of the specific energy is the velocity head. So this isn't exactly sketched to scale, because the energy grade line wouldn't be that much higher above the water surface. If it's critical flow, then that's 2/3 of the specific energy. But the point that this is making is that in theory, as water flows over a Broad-Crested Weir, you're not losing any of the total energy. That the total energy is constant. But there's this exchange between velocity head and depth. But the purpose of a Broad-Crested Weir is to quantify the flow rate, because you don't always know how much water is going through a channel. And there's different ways to quantify the flow rate. You could put a probe down into the water and measure the velocity and then multiply the velocity by the cross-sectional area. That's one method. But another method is to know a known depth, and then you'd use the cross-sectional area along with the known depth to calculate the flow rate. So these Broad-Crested Weirs are used to regulate and quantify flow, but the disadvantage with them, just to put it on your radar, is that there can be the accumulation of trash in the upstream area. And so like this front face is a place where if there's like sediment or debris washing downstream, it can get kind of stuck upstream of that Broad-Crested Weir. So that's the disadvantage. Now here's the equation that describes the hydraulics of a Broad-Crested Weir and how we can calculate what is the flow rate over the weir. Now there's a coefficient of discharge that accounts for the actual energy loss that we do see. Because in theory, there shouldn't be any loss of energy, but in reality, as the water is going through the transition, there's a little bit of turbulence that's induced, and there is some eddies and vortices upstream of the transition that the water is going countercurrent to the main flow direction, and all of that causes a little bit of energy loss that's accounted for in a coefficient of discharge. And so the overall equation here says that the flow rate through the channel is going to be this energy loss coefficient of discharge multiplied by B, which is the bottom width of the channel. And what we're assuming here, just for simplicity for now, is that it's a rectangular channel. And so the bottom width would be equal to the top width. So it's the width of the weir, square root of 2, and then 2/3 h. Remember, that is the critical depth. And so that's why we have 2/3 h to the 3/2 power. So we're estimating the flow rate by looking at the amount of energy that there is as it goes over the obstruction. So in practical terms, we can estimate the coefficient of discharge by the ratio of the depth of the water above the weir relative to the height of the weir. So you'll notice here that we measured the height of the Broad-Crested Weir, so that's the height of the step. In previous days we've looked at a delta Z is what we've called that. So the coefficient of discharge is a function of the height of the specific energy above the broad-crested weir to the weir height itself. Now, it turns out that the coefficient of discharge under most circumstances can be estimated more easily than that. It converges on a typical C sub D value as long as the weir height isn't too extreme. So this is the equation that you can use to calculate what's going on with a broad-crested weir. Now the other type of a weir that is used for flow regulation and estimation is a sharp-crested weir. So this is kind of like the spillway that we were looking at before, except for this time it is an actual physical sharp-crested weir. It's not that there is a spillway after this, it's just actually a sharp crest. And so again, we're using specific energy to ask the question, between two locations, how is energy being exchanged? And remember, we have this, we would use a weir to regulate the flow and to quantify it. And so as the water is flowing from 1 to 2, the elevation is decreasing and the velocity is going up. And so the exchange of specific energy is just between water depth and an increase in velocity at location 2. So at location 2, the elevation above the crest is 0, but now it has additional velocity that it didn't as the water was approaching the sharp crest. So what we can do is assume that the elevation of the water at location 2 is 0, because we're going to use the height of the sharp-crested weir as our elevation datum. So we're saying let's let this datum represent 0 elevation. So for 0 elevation, then you can use this device to find out what's the velocity of flow over the sharp crest. So it's equal to the depth of the water times 2g plus the velocity at 1 squared, and we take the square root of everything. And so if you assume that the height of the water from the bottom of the datum up to the total energy line, which is the elevation and the velocity head, then it's the square root of 2gh. So we've seen that before, square root of 2gh. You've seen that in the orifice equation back in fluid mechanics, and the same thing holds true here, that the velocity of the water as it's flowing over the weir is equal to the energy that drives it. Now, energy losses occur, and there's a discharge coefficient for a sharp-crested weir in the same way that we have a discharge coefficient for a broad-crested weir. And so the ratio of the height of the water to the height of the weir is how we estimate the coefficient of discharge. And so here in this formula, where we need to estimate the coefficient of discharge that goes into this flow equation, you'll notice that h is the height of the water level upstream above the weir crest. And this is what we call a suppressed weir. And the terminology is a little bit strange. It's the full width of the channel, and they call that a suppressed weir. If the weir isn't the entire width of the channel, then that's contracted, and I'll show you a different equation and how we correct for that in just a moment. But this assumes that the entire rectangular channel, water is flowing over the top of the weir across the entire width of the channel. And so it's going to depend on the width of the channel. So here L, if the channel width and the weir width are the same, that's the definition of a suppressed channel. So L would be equal to the width of the channel, so B. H is the height of the water above the crest. And then for this equation to be valid, there is an upper limit to how large H can be. So the height of the water over that sharp-crested weir can't be greater than double the weir height. But it's better, and you have more accuracy, if the height of the water above the weir is kept to less than 40% of the weir height, is what that comment says at the bottom there. So on the following slide, what we're going to do is combine a lot of constants together. So we're going to combine together the discharge coefficient, we're going to combine together the 2/3, and we'll combine square root of 2gh, and all of those constants together will be wrapped up into a simpler coefficient. And so that's what this is, where we're saying if you assume that you go with a really low water height to weir height ratio, meaning less than 10%, and that's typical. You really have to have super high flow rates to get a lot of weir height of the water over the weir. So under most conditions, the typical discharge coefficient is going to be 0.62. So we're saying that, you know, you solve this equation, the C sub D equation, most of the time your discharge coefficient is going to be 0.62 under, you know, the typical water heights that you would get over a weir. So for that, combining together that typical C sub D and then 2/3 square root of 2gh. So for traditional units, then this coefficient becomes 3.32, or for SI units it's 1.84. And then the only other thing that would dictate what flow you can get over a weir is the width of the weir, L, and then the height of the water, H. So this is the equation that you use in the homework problems that go along with this material, is you know, for a typical H to Z ratio, and then you have to keep track of, you know, is it a question that's asking for units in feet for the lengths or meters for SI. Now this is the other kind of a weir equation. This is a contracted weir. So remember, suppressed was when the weir is the entire width of the channel. So your canal is 5 meters wide, then that would mean the weir needs to be 5 meters wide for these equations to apply. But if the water is approaching a narrower weir than the channel width, as is the case here, in the top view you can see that the water is flowing towards this weir and it has to contract before it goes over the weir. In a situation like that, it ends up that there's some ineffective area, that there's not much flow along these edges on the left and on the right. And so because of the ineffective area, we have to adjust the Weir equation with L prime. So it's the same equation as before, a C value, L, and then H to the 3/2, but the difference being that now L, instead of being the actual physical width of the weir, you're calculating an effective flow width. So you're calculating L prime by subtracting out some segment of the ineffective flow area. Okay. Any questions about the Weir equations? All right, so that's all I have for you today. Just remember that the exam on Wednesday, you should be checking your email or look on Blackboard at 1 o'clock, and then you've got until 3 to submit that. If you have any questions as you're preparing for the exam, feel free to send me an email, or I can stick around here in this classroom after class if you have questions, or you can hit me up for a Zoom meeting. So that's all I got for you today. Hope you have a good one, and I'll see you for class on Friday because we'll be having the exam on Wednesday. Take care.